No, we don't need that. Okay. So our technology really stems from a growing interest in biodegradable polymers over the past couple of decades. So biodegradable polymers are really of interest for quite a diverse range of applications, everything from more environmentally friendly food packaging to quite an array of biomedical applications. So for example, they can serve as scaffolds for growing new tissues in applications in regenerative medicine. We can also use them to deliver drugs. They can package up the drugs and deliver them more selectively to their target in vivo. So over the past couple of decades, there's been really a lot of progress in this field, and most of this has been done with a class of polymers that are called polyesters. And so these polymers do many things well, but one of their limitations is that they degrade by a series of random cleavage events. And so this is very difficult to control, and in particular to trigger or turn on or turn off. And so our technology was really developed to address that limitation. So the concept of our polymers is to have a backbone that's inherently stable in the presence of an end cap, so something that we put at the terminus of the polymer. But when this end cap is cleaved, it initiates really a cascade of events that basically depolymerizes the polymer, kind of an unzipping effect. And we can design and incorporate end caps that are responsive to a wide range of stimuli. So for example, pH, light, heat, enzymes. If you can think of a stimulus, we might be able to develop an end cap to put on one of these polymers. And so there are a few of these polymers that have been developed in the literature, but some of the problems are that we would require multiple steps to make the monomers, and so this then becomes expensive. And these polymers typically degrade, releasing species that might be toxic. And so that's not good, especially for biomedical applications or if we want to put this in the environment. So the specific technology that we are focusing on with this innovation is a class of these depolymerizable polymers that we call polyglyoxylates. And they have a few key advantages over other analogous systems. So one is that ultimately the degradation product is something called glyoxylic acid hydrate. Don't worry about what it's called, but the key thing is that this is actually a metabolic intermediate in many organisms like plants and bacteria. And so it should be non-toxic and readily assimilated into the environment and converted to CO2. Another key advantage is that actually ethyl glyoxylate, which is a molecule that we can use as one of the monomers to prepare these, is commercially available. And so that provides us with a rapid access to these polymers, which people didn't have before. Another key advantage is because of the way that these polymers are structured, we can also tune them by incorporating different monomers or combining them with other monomers. And so that combined with the end cap gives us a lot of versatility to potentially use these for quite a wide variety of different applications. So I'll hand it over to Patrick.
So there's no doubt that biodegradable polymers are a hot topic. It's a massive market at 3.5 billion globally. As Dr. Gillies mentioned, there's lots of applications for these in packaging and agriculture, fibers and injection molding. You know, there's problems associated with all the current biodegradable polymers, such as they degrade randomly. They all leave some sort of plastic residue that's left in the environment, and they take a long time, and they can't be controlled. And that's really what this technology is addressing. So the three takeaways there are the biodegrading can be triggered, the polymers can be tuned, and the degradation products are essentially non-toxic. So those are the three selling features of this technology. We have a PCT application, so it's generally well protected. We just received a search report, and we had very favorable results. So there's a very high probability that we'll have some good IP protection around this. And in terms of going forward, a good plan in my mind is really one that's driven from the market need and the application. So what is the industry problem that you're trying to solve? You're going to need an understanding of what the material properties of that solution is going to look like, and since the polymer is tunable, what is those properties that you need? And then just a solid plan of how you're going to move this from the lab to industry. So thank you very much.